Alright, this is the Unit 25 Part 1 video. In this video we're going to discuss the nervous system and the endocrine system. Both of these body systems are the ones that our body uses to communicate with different parts of the body, so they're both very important in what they do. You need to make sure you're writing these notes down in your journal, recording everything you see on the screen, as well as anything else that I write down. Right, we're going to begin this discussion about the nervous system. So the nervous system is pretty much involved in every single reaction that you're going to have. Okay, every body system is going to be somewhat involved in the nervous system because our nervous system is basically what controls the body. Okay, because this is going to be including your brain and your spinal cord, which are going to be the ones that, the main organs that control what you do and how you do it. So one of the main jobs of the nervous system is to help maintain homeostasis, which is internal balance within our body. It allows us to be able to respond to stimuli very, very quickly. Okay, so we are able to respond fast, and a lot of the times we can respond so fast that we don't have to actually think about it or process it. This is due to the fact of a direct connection pathway of neurons. So a neuron is a nerve cell. These are specialized cells whose job is to send signals from throughout the body. All right, so the neuron is the basic unit of the nervous system, or the nervous cell. And you will need to know the parts of the neuron, because the way the neuron is designed is very, very important to how it works. So our neuron has actually three basic parts. It has dendrites, a cell body, and an axon. The dendrites actually look like finger-like extensions coming out from the cell body, and the axon actually looks like a tail extending at the end of it. So that's how you're going to tell the difference between our dendrites and the axon. So our dendrites, their job is to be the receptors that receive the stimulus from the external environment. So the dendrites, if you look at this picture I have here, are these extensions down here coming out from our cell body. And so these are actually going to be able to detect the stimuli from the next neighboring neuron, and it's going to be what accepts the signal, okay, from the neuron. So it accepts the signal, kind of like your fingertips accept signal from external areas. The dendrites are like the fingers of the neurons, so it's what receives the stimulus. And then that stimulus is then going to travel into our cell body. So our cell body of our neuron is what houses all of the organelles for the neuron. It has the nucleus, the mitochondria, and all the other organelles that a cell needs. And so it's going to be carrying out the basic life functions of our neuron. So our cell body is this region in here. In the middle, you can see on one side we have our dendrites extending, and on the opposite side we're going to have our axon. So the cell body is where we have all of those important organelles so that our cell can live and function like it needs to. Alright, the axon is important. Unlike dendrites, where we have lots of different dendrites, in axon there's only one per neuron. Okay, so it's this long tail-like fiber that's extending away from the cell body in the opposite direction of the dendrites. And its job is to transmit the impulse away from the cell body towards the other neurons. So the signal comes in here at the dendrites, it goes through the cell body, and then it's sent down the axon to the end where it's going to be converted so it can be sent off to the next neuron. Since the axon is carrying an electrical impulse, right, it actually has to be insulated by something called the myelin sheath. And so the myelin sheath is, if you look at these pictures, it's these little orangey, creamy looking things that cover up the fiber. So think about it this way. When you have your phone charger and you plug your phone charger into the wall, are the cords, the wires just exposed, or does it have an insulator or a cover over the wires? Well, hopefully, if your charger is correct and not going to kill you, you have an insulator or a cover over the wires, right? That way we can A, protect ourselves, and B, keep the charge on the wire. Okay, because if we don't have an insulator, that charge can jump off and go into other things that we don't want to go into. We want to keep that charge on the wire so it can go from the outlet plug in the wall down the wire all the way to our phone battery and charge our battery on our phone. The same concept goes here with the axon. The myelin sheath is like the cover or the outer layer of that phone charger, okay? It's covering up the wires so that we can keep that charge on the wire and it's not going to be jumping around and going off into the wrong place. Now, another reason the myelin sheath is important is because it's going to increase our nerve impulses. Because you can see here we have these gaps. These are actually called the nodes of Rainier. You don't have to know that, but we have these little gaps in between our myelin sheath bundle. And what happens is this signal can actually jump from one gap to the other in the way this is designed, so that instead of having to travel the length of the whole axon, it can go bounce, 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 and then be at the end. Alright, so it'll be a lot faster. Alright, so here's the pathway of the signal. I've kind of already gone over this, so we will read this again together. You need to make sure you write this down or paraphrase it in a way that you understand. So, the first step is that our dendrites are going to receive a signal. So, if we are looking at our neuron, here is our cell body, dendrites. Are coming out from the cell body, and then we have our axon, and then we have our axon terminals down here. Alright, so here is our neuron. So dendrites receive the signal. So signal comes into the dendrites. The signal then moves from the dendrites into the cell body. From the cell body, this impulse is then sent down our axon towards the end. So pretty easy. Dendrites to cell body to axon. Okay, notice at the end of our axon we have these little things that branch off. They look kind of like dendrites, but they are not. These are actually called axon terminals. And it's at this point that that signal goes from a electrical signal into a chemical signal. So you need to make sure you note this. And this chemical signal is actually called a neurotransmitter. Okay? And so the neurotransmitters are what's going to be released into the synapse. So the synapse means, what I'm referring to there, is that over here, next to this, next over here to our little neuron that I've drawn, let's draw the neighboring neuron. So we know there's going to be another neuron over here. It's going to have some dendrites that are going to be sending out like this. Now, these dendrites and axon terminals do not come in physical contact. Okay, so we cannot just make an electrical impulse connect to it. Okay, they are not connected. Instead, we have an area in between the neurons called the synapse. So this area here is called the synapse. That's the synapse, right? It's the space between two neurons. And this is the area where we're going to release those neurotransmitters. So when we release the neurotransmitters from the end here, so when these neurotransmitters get released from this end, I can get something here. Let's see here. This won't work good. The neurotransmitters get released here, and then they're going to flow into they're going to be received by the dendrites, and the dendrites will then convert it to an electrical impulse. Okay, so here's a better picture than what I just drew. So the pathway of the signal, we have our dendrites to our cell body, to the axon, down the axon terminals. The axon terminals are where it is going to be converted into a neurotransmitter, and those neurotransmitters are then going to be released into the synapse. All right, so again, here we go. We have from this side, it's dendrites. So dendrites receive the signal. Signal travels through the cell body, down the axon to the axon terminals. It is here where we convert that to a chemical signal. So every part before here, this whole area here, this is all electrical. But it's the very end, this end is where we get the chemical signal that's going to be released, okay, into the synapse. All right, the electrical impulse is actually the result of those sodium-potassium ion pumps that are actively pumped across the cell membrane. So if you think back to when we talked about active transport, sodium-potassium pumps, these were an example of a protein pump. Okay, so these sodium-potassium pump, remember, here's our membrane. We had two pumps here on here, and we pump out 3 sodiums, and we pump in 2 potassiums, and so we get an unequal distribution of charge, which creates a concentration gradient, so that whenever we stop pumping, these are going to automatically flow down the concentration gradient. So when we stop pumping these out, okay, what's going to happen is these are going to rush back this way, and these are going to rush back this way. So we're going to see a giant flip of the switch, basically. So they're going to be flipping, and they're going to be rushing across the side to the other side. So when that happens, that causes a signal to be sent down the axon. Now, when we get to the end of the axon again, remember this electrical signal is converted to a chemical signal, and those neurotransmitters are what are going to be released into the synapse. So here's a picture, an up-close picture of our synapse. You can see this is an actual axon terminal here. This is the space. There's a synapse, and here are the dendrites of another neuron. And in between here, you can see those little bitty dots. Those are little neurotransmitters. And they're actually going to be released out of this axon terminal through a process, a type of active transport, which we learned about, called exocytosis. So see, we do learn stuff for a reason, because it comes back. So these neurotransmitters are released through exocytosis, and then they actually have receptors here on the dendrites of the other neuron that accept those neurotransmitters, and then the dendrites then send the signal onto the cell body so that it can send the electrical impulse down the axon. We have 3 different types of neurons: sensory neurons, motor neurons, and interneurons. A sensory neuron, these are the ones that are going to be detecting our stimuli and transmitting information from our body to our brain and spinal cord. So for instance, this is going to be like the neurons in our skin, the neurons in our muscles, joints, sensory organs, and internal organs. So for instance, these are the neurons that allow us to be able to see, smell, touch, hear, and taste. All of those senses, we rely on the sensory neurons to be able to do those. Motor neurons are going to be the neurons that are going to be sending impulses from your brain and spinal cord to your muscles. So these are neurons that allow us to be able to move our muscles, and which then allows us to be able to move our bodies, right? It's pretty important. And the interneurons are special neurons that are a part of the reflex pathway. So they're going to connect our sensory neurons and our motor neurons together so that we can have reflexes and react quickly in dangerous situations. we call this the reflex arc. And so the reflex arc consists of all 3 neurons. And what's going to happen is our stimulus is going to be detected through a sensory neuron. Then it's going to move through an interneuron in the spinal cord, then back to a motor neuron, which is going to tell muscles to contract, and it's going to move the appropriate muscles. So for example, let's say we have a pan on a stove, and here's my fire underneath it. Okay, here's our burner. Really great artist here. And here, the hand accidentally touches the hot. Okay, what's going to happen is this hand is going to immediately jerk back. You don't have to think about it. So if you accidentally touch a hot surface, you don't sit there and hang out with your hand on that hot surface all the time. You just touch it and then you quickly jump back, okay? This is because of a reflex arc. So sensory neurons in your fingertips send a signal to an interneuron in your spinal cord, which then sends a signal to the muscles in your fingers to move your hand out of the way. So it all happens almost instantaneously, and we don't even have to think about it. All right. So that is the nervous system. Again, the nervous system is pretty much involved in all body system interactions. It's going to be a part of it because your nervous system is what controls your body. It's like the king of the body. So let's get into now the endocrine system. Our endocrine system is the same type of system in that it's a messaging system or a signaling system. But our endocrine system is going to use chemicals instead of electrical impulses. So the endocrine system uses chemicals to send message. Instead of neurotransmitters, we call these hormones, right? I'm sure, when you think of hormones, you think of, teenagers going through puberty, your hormones start raging, blah, blah, blah. That's where we mostly hear it. Hormones are a lot more important than that, okay? So we have hormones for every single type of reaction in our body. And hormones are important for helping us to send signals that need to take a little bit longer than the nervous system. So these signals are going to be very specific. You're going to have a specific goal in mind. Hormones are going to travel through the circulatory system towards glands or organs. So unlike the nervous system, the endocrine system does not have a direct connection pathway. Instead, it's going to take advantage of our bloodstream. And those hormones are going to travel in our bloodstream until they reach their destination. And we have 2 types of hormones. We have steroid hormones and non-steroid hormones. And this is just basically talking about how they are designed, how they look. Steroid hormones are going to travel to the target cell, diffuse across the membrane, and then they're going to go into the nucleus, influence DNA, and cause certain proteins to be made. So, for instance, if we are lacking a certain protein, the brain may signal the hypothalamus is the gland that's in charge of the endocrine system. It may send a signal that says, hey, we need more of this protein. So it releases a hormone so that it can tell the certain types of cells to start making more of this protein for the body. Non-steroid hormones, however, actually do not ever enter the cell. Instead, they're going to attach to a receptor outside the cell, which is then going to cause a cell to take in the signal and begin making the change or producing whatever it needs to produce. Endocrine glands are our glands that are going to be producing hormones, and we have lots of different glands that do this in our body. Some of these include the hypothalamus, the pituitary, the pineal, thyroid, adrenal, pancreas, ovaries, and testes. All of these glands produce hormones of some kind. Both nervous system and endocrine systems are important in maintaining homeostasis, and they're going to be communicating through the thalamus and hypothalamus, which are actually different parts of the brain. So for example, when you smell food, you have olfactory receptors, which are neurons in your nose that smell the food, and so they send that signal to the thalamus right in your brain, which then sends out a signal to the muscles to start moving you to the food. Okay, that's nervous. Now, also when that happens, your endocrine system starts releasing hormones to prepare your stomach and digestive system for a meal, right? So your stomach might start growling, and your stomach's going to begin to get ready to digest the meal that you're going to be eating. We call the pituitary the master gland because it's going to be controlling the hormones released from all other glands. And in the endocrine system, we have two different types of what we call feedback loops, a negative feedback loop and a positive feedback loop. The negative feedback loop is controlled by the endocrine system. The best way to describe this is it's like a heating or cooling system in our building. So in the classroom, we have our thermostat set to a certain temperature, okay, maybe 70 degrees. And this is a desired temperature that we want our classroom to be. So when I have it set at that temperature, if it gets too hot, then the thermostat is going to tell the air conditioner it needs to come on and cool the building down. So then once we reach 70 degrees, the air conditioner turns off, right? And then we're good. Okay. Now, if it gets below 70 degrees, then we're going to have to turn on the heater. And the heater is going to warm the room back up to 70 degrees. Either way, once we reach that desired outcome, once we reach 70 degrees, we are good. The reaction stops happening. Okay? So a negative feedback loop, the same kind of thing is going to happen in our body. This is going to mean that once we reach a desired level, then it's going to stop. It's not going to be needed to do anymore. So for instance, if a hormone level is too low, it's going to send messages to the target gland to start making more. That gland will start making more hormones until the level is raised. Then, once the level is raised to the correct level, then it's going to send another signal which will turn off the gland. So this is an example of negative feedback loop. Now, if the negative feedback loop doesn't work correctly, we can have different diseases and conditions that can occur. One type of disease is called diabetes. So normally after you eat and your glucose levels in the blood rise, your body actually naturally releases the hormone insulin. Okay, insulin is a hormone produced by your pancreas that tells your body to take in the glucose or the sugar from the blood and break it down. So if you don't have enough, so what should happen is that your body takes in the sugar and then your sugar levels go down, okay, because your cells are taking in the sugar from the bloodstream. However, if you are if you're diabetic, what happens is your body does not produce enough insulin. Okay, so you don't have enough insulin. So that means that there is nothing to tell your cells to take in the sugar from the bloodstream. Okay, so that's why sometimes diabetics have to take artificial insulin in order to be able to tell their cells to take in the sugar from the bloodstream. So the opposite effect of insulin is glucagon. So glucagon means glucose is gone, and so that means our blood sugar is too low. So if we're in between meals, say we had breakfast at 7, lunch is until noon, it's about 10 o'clock, and our blood sugars are getting low, what's going to happen is your body's going to release the hormone called glucagon, which is going to signal your cells to start breaking down its glucose storage called glycogen, and it's going to turn it back into glucose, and this will cause our sugar levels to rise. Remember, in both of these instances, these reactions are only going to happen until our desired outcome is reached, and then it's going to stop. So again, in diabetes, a person who does not generate enough insulin is going to have to be able to take insulin so that their bodies can function correctly. Right. A positive feedback loop is the opposite of a negative feedback loop. So instead of a reaction stopping at a certain level, the reaction is actually going to be amplified. The best example of this is childbirth, right? So for instance, when the hormone pitocin is released into the bloodstream, this causes the uterus to begin to contract, all right? That's the first step of labor. And as the uterus begins to contract, this signals to the brain to release more Pitocin. So more Pitocin is going to be released, which is going to cause the uterus to contract even more. Right? So in childbirth, contractions start off, very not very intense, and they're very far apart. But as you progress through childbirth, they become closer together and they become more intense in pain. And this is because of the positive feedback loop. Because as the more contractions we have, the more Pitocin that's released, which causes then the contractions to become even more intense. And then the more intense the contractions, the more hormone that's released. So it's constantly feeding this positive feedback loop, making this reaction happen even more. It's amplifying the reaction. And this is going to occur until the child is born. Right? So this is the best example of a positive feedback loop. All right. This should be the end of our Unit 25, Part 1 video notes. Make sure you have everything written down, and if you need to go back and rewatch any parts, make sure you do so.